Hi everyone. I think this is going to be the second half of Module 12, and it's going to be off the textbook because I'm going to show you how the data can be sent and recorded on your FPGA using this stuff called blockram, specific for audio files, and then also going to talk a little bit about data storage and the history of that. It's just hopefully you probably know some of this already, but hopefully this kind of gives you kind of a historical perspective on how audio storage actually was first made in the 1800s. Okay, so let's talk about an audio file, right? Sound wave, right? It's basically just pulses of pressure, sound at air at different pressure that's created by basically my vocal cord up to my mouth, and then I'm making a little pressure wave that's pushing the sound around, so that way it oscillates back and forth, and then it travels at the speed of sound into people's ear, and then they have to listen to me. Okay, what this looks like as data, as information, right? Um, is don't worry about the Python code, just in case people want to look at this. Okay, these will start looking like little pulses. So this is when I'm like saying something, I'm being quiet, saying something, I'm being quiet, right? This looks like little lumps of stuff, so it's really hard to look at. But if we zoom in to one of these lumps, it looks like this. Okay, so it's going up and down, up and down. And this is actually a linear combinations of different frequency. When I speak, I don't just talk in one frequency. I think for a male voice is probably like about the center frequency is about 350, but then I would have stuff that's at 360, 340, 410. And if I speak like this, right, then I'll have a frequency at like 500 and 600, something like that. Okay, so when people speak, they are actually creating sound at many different frequency, and then it's this linear combination of all these frequencies and their amplitude added together, right? That what produces the particular sound that you're hearing. Okay. In this case, this is a 8-bit, meaning it can go from 0 to 255 hopefully. And this is actually an 8 kilohertz audio file. So 8 kilohertz, meaning that's the sampling rate, right? So for every 1 second, there are 8,000 sampling of that sound, okay? Right? So each data point is separated by 0.125 milliseconds. Okay, so how do we get this information onto your FPGA that you're going to be doing in the lab? Okay, um, typically on a MP3 player or your phone, mostly. Um, these devices are internal, so this is like your SSD or an SD card that you use in order to store this information, and then those are stored in like some file format, um, and that's usually nice and compressed, and therefore is good for storage sake. Unfortunately, we're not going to use the MP3 format directly because that requires some conversion, some decoding from the MP3 format into the raw format, which is actually what's drawn here. This is a raw audio file. It's literally just telling you the amplitude of the wave as it goes up and down. We're going to be using this. Okay, and there's a way for us to store this on our Arctic 7, which has these things called block RAM. Block RAM memory resource, yes. So block RAM here, right? So for our 37, right, we have 50 block RAM, and each of them are 36 kilobits each. Okay, so you can multiply them together. So that I guess that's 1.8 megabits that you can store onto the FPGA. So these are not exactly like the registers or the flip-flops that we've been talking about. They're slightly different. They're basically information. They are basically data, uh, NAND type flash data that's been stacked in multiple layers. So they are slower. Um, but if you're reading them out sequentially, it's actually pretty quick. But there are slightly different type of memory. So you can see that, it's not just block RAM, but you also have, regular distributed RAM here, which is only 400 kilobits instead, right? So it says they use things that are, these will be faster, but the block RAM is going to be what we're going to use in order to store these music files into your FPGA. Okay, you can actually view this if you do the implementation design map. If you program a lot of block RAM here, you're going to end up using a lot of this. And I think all this blue stuff is actually being used. When the reason it's called block RAM is because once you use one of them, the entire one is dedicated for it. You cannot. So they come in little chunks of 36 kilobits each. So you cannot get 1 bit of block RAM, for example. You have to get them 36 kilobits at a time. Okay. Yeah, even I think I highlighted this where this is a block RAM on your device. Okay. Oh, and I did the calculation. There's 50 block RAMs, each of them 36 kilobits. So we can store 1.8 megabit of data. And these files are going to have to be smaller than that. That's basically the limitation for us to store things on the block RAM. Okay. The name of these files indicate how many data points there are. So if you have 75697, that means there's actually 75,000 rows of data. That tells you the amplitude of your wave that you're trying to deal with. Okay. And so let's do an example where let's start with a smaller file, which is about 20,000, right? So 20,000 rows of data, and then we're doing 8-bit music. So that means each of them will take up 8 bits. So that means you need 160,000 bits, okay, of block RAM. Okay. And then since they come in chunks of 36 kilobits, you need at least 4.4. But then since they come in blocks of that 36 kilobits, it actually takes 5 block RAM. So you're using about 10% of your block RAM allocation by programming this particular file in. Okay. The way you send that data into your FPGA, programming it into your FPGA, is by using this thing called the memory. Actually, let's go. It's going to make more sense because I have to go down in the bottom and then describe actually what's going on. Okay. So you're using this $, which is a special command that's been written in, and it's called read mem h. The h means it's a hexadecimal. So these are programmed in hex mode. That allows us to store things, well, 8-bit at a time. So there's going to be 2 characters where you have one hexadecimal number, which is 4-bit, and then another hexadecimal character, which is another 4 bits. So you have 8-bit together. And that's the format that these are made in. You could make it into decimal, but then you're going to run into some inefficiency because 10 does not divide into 2 very well, where 16 does. Okay. And then so this little read mem command allows you to read out basically the entire thing into some memory bank. And what memory bank are we talking about? This memory bank is a 8-bit memory bank, right? Of the size, whatever the memory size is, how many rows of memory. But we want to subtract 1 from it. The reason we subtract 1 is because remember when you have 7 0, right? It does not mean 7 bits, this is actually an 8-bit, right? So you always have to subtract 1 from it. And then colon 0 gives you the all the way to 0, so that tells you the size of this memory bank that you're making. Okay. And what that does is basically put this entire text file into memory here. Okay. And then you can declare a local parameter called memsize, so you know that you don't have to modify this line. You're just modifying this to, oh, I want to store things that has the bigger file, right? So that corresponds with this. That corresponds to this. Oh, I guess we got that copy twice. That's okay. Okay. All right. So that's how you store your music into these block RAM memory using this read mem hex command. Okay. The way you would play this back out is by using addresses, because, right, when you play the music back, you don't play the entire wave back all at once. You play it one roll at a time. You start. Let me go back up here where the picture is. Right, you start here. All right, whatever that voltage is, and then you keep going. Then you go to the next point. You go to the next point. You go to the next point. It's just sampling, sampling, sampling. Right. So you're changing the voltage as a function of time, one voltage at a time. Right. So that's what this memory address allows you to do. Okay. Because when you hit play, you can have a little button called play, or it might be like the middle button, right? What you want to do is you want to use a slow clock, and this is going to be the frequency of the audio you're using. And I think these are programmed to be 8 kilohertz. Okay. And then what it does is that it iterates through these addresses one at a time. Okay. And it increases this address one at a time. And you're connecting, right, your flash clock, which is 8 kilohertz times 8 bits, so that's 128, right, to whatever address gets incremented here. The memory came from your block RAM, right, and you're passing it. So this is the 8-bit data, right? What's called, I think it was called XN, like that. That's the 8-bit number that you're passing in. You're passing in the clock, and then JB2 is basically the voltage output that's going to give you this wave that comes out as analog. So you have these digital information in here, right? You put it in some clock, and then the analog data comes out, which is pretty neat. Okay. All right, so that's how you deal with the MP3 kind of clock. Oh, sorry, not 128. This is 256. Yeah, so the file is actually, so 8 bits 2 to the 8 is actually 256. Sorry about that. Okay, so that's how you implement the sigma delta pulse width modulation to convert your digital data, right, into analog waves that a computer speaker can handle. Okay, right, and you can do this using this sigma delta pulse width modulation, or you can use the simple pulse width modulation that you make for yourself. At this point, you will not hear the difference, but there are some advantage for the sigma delta over the simple. Okay. All right. At this point, I just want to give you guys like a kind of a quick history on how these information gets stored besides our FPGA. And this goes back to 1887, when the first record player was records were actually made. Okay. So I don't know if you've seen these things before. I always wonder, like, back in the 1880s, there's no electricity, right? And then there's literally a little handle where you wind this up by, and then it's basically a thing that spins this disc called a record. It's a recording. And the way this works is that basically when you record a record, right? So if you zoom into this record, there are grooves in here, right? And then there's a needle, right? And then basically when you're recording, you're making this dent up and down, up and down, up and down, and bigger and smaller and at different frequency. And you're literally physically engraving your your sound wave into the grooves of this record, which is pretty neat. I didn't know about this until I think I started teaching this class. And when you play it back, the needle basically goes on here and it's not edging it anymore, right? It's just kind of sampling it. And then as this needle go up and down, it creates a little vibration here, and then that vibration is amplified through this little megaphone thing. It's called a gammaphone. And yeah, and then if you look at a record very closely, you can physically see these grooves in here, which is kind of neat. Okay. Since 1830s, when there's vacuum tubes are basically popularized, right? Now you can amplify this, because what you would have to do is basically stand next to this device and then be really really quiet in order for you to hear it, because you're literally just hearing the scratches made between the pin and the record when you're listening to this. Okay. And then when you can amplify it, now you can play it through these speakers. You have a little dial, you can turn up the volume and stuff like that, which is kind of how records are. If you still have a record player today, most likely you're going to be using some sort of amplifier to play back the sound instead. Okay, so the way that these records are made is literally using a lathe, which is something we have in the machine shop. I didn't know about this. And so what they do is they basically etch in these records what the pattern is. Okay. But since like I think the 60s, these are actually stamped, because it in order for you to lathe a 1 hour record, it takes an hour to do that, right? But so what they started doing is they started making records by just pressing it, meaning you have a master, which is made of steel or aluminum, right? And then this is called a father disc for some reason. It's made of aluminum, and you're literally just stamping the you have the mirror pattern of it, and then when you stamp it, you get the regular pattern back out on vinyl, okay, which is a much softer material. It's basically plastic, okay. And then this room is basically basically pop pop pop, like, so every second you will have a new record that pops out, as opposed to waiting an hour. Okay, that's how we record sound before the computer age. And then people started, well, why not use, instead of using the physical etching and the grooves and the pits to record this information, you can use magnets. So this is basically how a magnetic storage device work. Okay. So here's a little hard disk, and in this hard disk there's a head, and that's what this corresponds to. And then the discs themselves are just material that can be magnetized, and they're kind of edged in a way that's in a circular pattern, so that when you run the disc around, you get the same read, and then you move the head over a little bit, then you get the next one. Anyway, so let's just talk about how this works, right? So when you have the read head has a writer and a reader. Okay, the writer has a little coil, a little solenoid coil around it. So when that turns on, it creates a magnetic field. I think it's usually pulling it upward. Okay, that magnetic field, when it's near this magnetizable material, it'll basically make the pole of that material, north facing or south facing, depending on the direction of the magnetic field. So if the magnetic field is going up, right? If the magnetic field is going up, it'll make it north. If If the magnetic field is going down, then it'll make this south pointing, and then it'll just go through that, and then you can read write to your hard disk like that. And then to read it, it's actually much simpler. You don't even need this little coil, right? As you move a magnetizable material around it, these little magnets now give off magnetic fields. So you put it close to it, you can actually sense whether it's a north pointing or south pointing magnet. And then as you read it, it'll tell you the ones and zeros. So maybe this represents 1, the south pointing represents 0. So you have ones and 0, ones and 0, ones and 0 coming out. Okay, and these are organized. This is one particular line information, and these lines are arranged into tracks where you have a bunch of tracks, maybe thousands of them along here, right? And there's actually also sectors, so there may be multiple heads that reads out different sectors, okay? And that allows you to organize different parts of your hard drive, okay? And that's basically how a spinning kite on a hard drive store information is, just a bunch of magnets, okay? With stuff that are easier, more even, you would think this is actually a easier technology to deal with. It's what we learn how to do, what we learn how to make in our class. You can make this yourself on your breadboard, or NAND flash memories. Okay, NAND flash memories, basically the very similar working principle compared to a NAND logic gate. This is actually a NAND logic gate, not a storage unit. Okay, the way this works is that you have a NAND gate, right? Remember, a NAND gate is that, well, when both inputs are low, that's when the voltage stays high. Okay, so when both of these are low, that means both these transistors are off, and then no current runs through. No current means whatever no current runs through R2. That means the voltage drop across R2 is 0. So whatever output here is going to be VCC when it's low. But when you open one of these gates, okay, well, sorry, when you open both of these gates, that's when the current's allowed to drain through here, and that draws enough current to saturate these transistor, and therefore, right, the output voltage here goes from high to low. Okay, right, so that gives you, ones and zeros there, but right, it's not permanent, right? You have to keep this VCC up, you have to keep A and B at the right states. So how do we make this into something that's non-volatile? So going from a logic gate to NAND memory, right? What you do is you add one little component here. You add a line here with a capacitor. Let's draw it this way. With a capacitor to ground, right? Some capacitor C. So how does that help? How does that make it non-volatile? Right. So let's think about the case when the output is high, meaning whatever the voltage here is basically equivalent to VCC. Okay. When this voltage is at VCC, right, that means here, right, the current cannot pass through this transistor. Well, it can go through this transistor if A is 1, right? Otherwise it cannot. Okay, so you have some voltage here. Okay, and this basically charges this capacitor so that the delta V here, oops, delta V across the capacitor, delta V across the capacitor is going to be equal to VCC. Okay, when the output is actually at 0, let's do that in black, right? It can discharge this capacitor so that, whatever delta V is basically becomes 0. Okay, And why you use a capacitor for this is basically you can store that little bit of charge here, right? And this charge can live there if you design these things right for years, right? Because what happened is that if you have a bunch of charge here, right? Plus, 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 plus here, right? These charges, right, is actually locked behind these two transistors, right? It cannot flow this way. And if B is off, right, it also cannot flow this way. So therefore, it allows you to kind of lock these charges between these two transistors, and that will allow you to charge and discharge it when you open and uses these NAND gates, right? But when you disconnect VCC and A and B from it, this charge basically gets stuck in there, and then it's holding that voltage approximately at VCC. It is going to drain over time, right? Because you're gonna have some current that leaks out of it, but right, supposedly, these little NAND flash memory can actually last for years. Um, okay, that's conceptually how you would make this, but engineering wise, you actually don't make it like that because it's just very inefficient. The way you would make NAND flash is by putting two N dope material and one P dope material together. So you don't even need two transistors, you just need one. And then what you do is you have this gate, right, which is made of semiconductor. You have an insulator between the two. What happened is that if you have 0, this is the inputs that you're dealing with. Okay. What happened is that charges will migrate from the center material down to the P substrate. So you don't get any voltage across this. Okay. But if your input, you set it at high voltage, high meaning like 5 volts in this case, right? What will happen is that you're basically going to be pulling electrons out of the P substrate into this middle section, but they are separated by this insulator, so they can actually not go here. But this insulator is slightly transmissive so that you can actually have the charge flow through here. And what that allows you to do is basically store the charge in here instead of being in a capacitor. So this essentially, this little conductor in here, right, basically is access the capacitor. And then when you disconnect from this, those charges are just stuck in there. It cannot, it slowly leaks back into the P substrate, but they designed it so this happens on the orders of years. And that's basically the working principles of NAND flash memory. Okay. I think I'm not going to go through the structure stuff because that's a little extra information that you don't need to learn about, and why MLC drives are slower than SLC drives and stuff like that. But so if you have questions about that, you're welcome to come and ask me. Okay. And that's all for the lectures this week. I will see you on Monday.